Hi, my name is Darius.
Hi, I'm Sarah.
Hi, I'm Philip.
In 2014, Rosetta, a space probe built by ESA, escorted Comet 67 for 2 years, with its main objective to study its composition, formed around 4.6 billion years ago. This analysis gives indispensable insight into the origin and evolution of our solar system. During the comet's orbit, the point at which it's found furthest away from the Sun is called the aphelion. Meanwhile, the point at which it's nearest is the perihelion. A large part of the Rosetta mission was spent accompanying the comet through perihelion, during which we focused our project on. Now let's take a look at the comet. A comet is composed of a large proportion of ice, which sublimes at high temperatures, such as those encountered near the Sun, releasing gases which make up what we call the tail of the comet. This process is referred to as outgassing. Near perihelion, this value is around 60,000 quadrillion particles per second. The solar intensity can be quantized by analyzing the flux at different activities for a range of wavelengths, as seen in this graph. In addition, due to the ionizing properties of photons at particular wavelengths, elements such as carbon dioxide and water in the comet's nucleus ionize and lead to the formation of oxynomial, hydroxide, and hydrogen ions, to name a few. Meanwhile, other photons are absorbed.
For the following explanation, the comet is located at the center of our coordinate system, with a nucleus of 2,000 meter radius. The Sun is located in the positive x direction, and the solar zenith angle is the angle made between the positive x-axis and a line representing the position vector of the point of interest. A solar zenith angle of pi/2 defines the terminator plane, or the yz plane. The latitude is the angle between the positive z-axis and the projection of the position vector of the point of interest onto the yz plane. The coma of the comet was modelled as a density distribution of water molecules, and for the purpose of showing the difference between symmetrical and asymmetrical models, two distributions were used. Well, the first was a simple radial inverse square distribution, dependent on total outgassing rate Q, cometer-centric distance r, and exiting velocity v. The second model builds on this by including a factor of the cosine of half the solar zenith angle phi, as well as a cosine scale, or asymmetry factor s, which is used to compute the normalization factor n, which ensures the outward flux remains equal to outgassing rate. This model imitates how a real comet would behave, where the column density is greater closer to the Sun. Column density is defined as the measure of the amount of intervening matter between an observer and the object being observed. In this project, it represents the number of water molecules per square meter in the terminator plane. We use two methods of finding column density. The first uses the three-dimensional coma model to integrate the number density directly along lines parallel to the x-axis. We may not, however, always have data about the entire coma of a comet, so the second method uses only the number density in the terminator plane to find a relation between neutral number density and commutative-centric distance. For a given y and z coordinate, or a given latitude, we assume this relation stays constant, and using substitution for commutative-centric distance, we can integrate this relation along a line parallel to the x-axis to find column density in the terminator plane. The plots currently displayed show the neutral number density and the column density in the z=0 plane, demonstrating the asymmetry of the coma model and how column density is constantly increasing in the negative x direction, which allowed us to identify incorrect functions which display decrease in the negative x direction behind the comet. When using the spherically symmetrical coma model, we found that both methods of finding column density gave the same results, as the first method finds the column density accurately by using the entire three-dimensional coma model, while the second method makes the assumption that the column density does not change with solar zenith angle, only latitude, which in the case of spherically symmetrical coma is true. For the asymmetrical coma model, when using the same color bar, it is clear that the second method predicts lower column density, which we found to be 15% lower at the respective peaks. This is due to the second method using the radial profiles from one solar zenith angle of pi/2, while the neutral density is greater at smaller solar zenith angles. This means that the second method cannot account for the increased coma density closer to the Sun and shows a lower column density than the first, more accurate method.
From the column density, which we can imagine as a number of particles along the line of measurement, we aim to get a quantity which is called the optical depth. The negative exponential of this quantity would be the proportion between the transmitted and received solar flux. As you can imagine, this quantity will be also dependent on the flux wavelength, and the relation between the column density and the optical depth is described by a parameter known as sigma ABS. Then for the optical depth bigger than 2, we can talk about the fully attenuated coma, where no light passes through the comma, and for low values we have so-called very attenuated comma, where we can calculate it from the exponential. So if we look at example of this column density of the asymmetric comma, and then we look at the sigma values measured in the lab, and let's say we focus on some arbitrary chosen value such as 30 nanometers, then we can achieve following profile of optical depth for this specific wavelength, and which we can see that is not fully attenuated. This would then result in the following relative source flux, which is just the ratio between the transmitted and received source flux. However, we do not have to stay restricted on the given wavelength, and we can put the wavelength on the x-axis and the x-dimension on the y-axis, and then plot different profiles for different distances from the nucleus. And we can see that as we get further from the nucleus, the optical depth is increasing, and so the comma is getting less attenuated. Those values are then used for calculation of production rate and possibly other quantities.
The electron production rate, as the name implies, is the number of electrons produced per second. Some of the sources we evaluated in our project were oxynomial, hydroxide, oxygen, and hydrogen ions. An example of a reaction that can take place is the formation of oxynomial and an electron from water, or similarly, hydrogen, an oxygen ion, and an electron from water. When calculating this rate, it depends on the attenuated solar flux, the photoionization cross-section, that is, the probability of an electron being emitted due to its state, and the neutral number density of the comma at that point, integrated over a range of wavelengths, from a non-ionizing short wavelength of 0.1 nanometers to an ionizing threshold wavelength in water of 98.2 nanometers. This would be summed up for all the different sources of electron production. These calculations were carried out under the assumption that the comma is in isothermal equilibrium and hydrostatic equilibrium, and that the ions that we were considering were singly charged only. A plot for each model representing an estimate of the electron production rate at varying cometocentric distances was made. Near perihelion, the electron production rate is very large. Billions of electrons are produced per unit volume every second due to the close proximity to the Sun. As expected, a rate of 0 is measured in the nucleus and at very large cometocentric distances, where the optical depth tends to 0, attenuating the incoming solar rays. These characteristics we were looking for allowed us to distinguish between erroneous and reasonable graphs. The rate for the asymmetric model reaches a maximum of 5, meanwhile the symmetric model of 6.5 billion electrons. For both our models, the peak value is exhibited along the northern and southern hemisphere of the comet. However, in the point furthest away from the Sun, the electron production rate is roughly 3 times larger for the symmetric model in comparison to the asymmetric model. In addition, at a fixed outgassing activity and wavelength, the maximum production of electrons was found to be located at a value of tau equals 2, in comparison to a value of tau equals 1 in planetary atmospheres. This relative noticeable differences demonstrates the importance of modeling 67P with its proper geometry, rather than assuming a spherically symmetric comma.